In this video, we'll look at several examples of logarithmic and exponential functions as a way to practice differentiating these functions using the shortcut methods that we've developed so far. So let's start off with these two examples. I've got one function that's defined as e to the minus x squared, and the other one is x squared e to the 2x. Okay, so I've got to use several of my shortcut rules here to come up with the derivative of these functions. So first of all, let's look at number one. If I want to find the derivative of y with respect to x, then I just go ahead and differentiate this using the shortcut rules that we know about. Remember, for exponentials in general, if I want to take the derivative with respect to x of e to the f of x, well, we take the derivative of that f of x, that comes down, and we're left over with e to the f of x, right? So in this case, I can identify that my f of x is the exponential up here. It's a function of x. It's not just x by itself. So I can just use my shortcut rule. This one's pretty straightforward. The derivative here of this function is going to be a minus 2x, right? So I get a minus 2x, and then I'm left over with just e to the whatever again, right? The function back over again. So e to the minus x squared. So there's the answer for that one. For the second one, however, I still need to use this rule because we have a function of x in the exponent. But also, notice that I have a product here. In other words, there's a product of two functions. So that means I have to use the product rule and my shortcut rule of exponentials. So let's go ahead and do that. So notice that for this one, first of all, I'm going to use the product rule. That's kind of the outside thing I'm using. And then interior to that, I have to know about the derivative of polynomials, the power rule, and of course of exponentials. So first of all, remember that when we're taking the derivative of a product, we take the derivative of the first function multiplied by the second function plus the other way around. So this is going to be the derivative of this first function, which is going to be 2x, multiplied by the second function, which is just e to the 2x, plus the other way around. It's the first function multiplied by the derivative of that second function. But in this case, the derivative of this function, we need to use this shortcut rule. So the derivative of 2x is just 2, so that comes down. That was my f. And I'm left over with e to the 2x again. Okay? And I could simplify this if I want. Notice that you have a common 2x and e to the 2x. You don't have to, but we could say, we could factor out a 2x e to the 2x. What's left over is, well, there's a 1 here and there's an x over here, it looks like. So that would be the shortcut. Using the shortcut rule, we could get the differentiation, or I should say the derivative, of this function. So let's look at some more examples. So notice that in this third example, I actually have a quotient of two functions. So not only do I have to keep track of the derivative of exponentials, that shortcut rule, but also I've got to use the quotient rule. Okay, so I get to use both of them together. So let's do this. Here's 3. So let's take the derivative of y with respect to x. And again, on the outside, you see there's a quotient. So that's kind of what I'm doing at first. And inside of that, I'm going to have to use the derivative shortcut rule for the exponential function. So let's go ahead and do this. Remember that there's a little way of remembering the quotient rule. It's the way that I always remember, which is low d high minus high d low over the bottom squared we go, right? So I'm going to identify the pieces of this. This is my low part. This part up here is the high. So I'm going to take low multiplied by d high. So low is x. D high, well, I'm just going to write it as the derivative right now. So it's the derivative of the high part, which is e to the x plus e to the minus x. Minus, so low d high minus high. Here's high, e to the x plus e to the minus x. D low, well, this one's easy. We can write this as the derivative right away because the derivative of x is 1. So multiplied by 1. Divided by the bottom squared we go, right? Over the bottom squared we go. So now, I'm just going to simplify this as far as I can. So the x squared remains on the bottom. And I just need to differentiate this to simplify. Well, remember that we know the shortcut rule for exponentials. In particular, d dx of e to the x, that one's easy. That's just e to the x. That's one of those very special functions where it is its own derivative. But here we have to be a little bit more careful. Notice that in this second case, it's not x anymore, but now it's minus x. So now it's a function of x. In particular, if this is my little f of x, we know the derivative of that is going to be minus 1. So, using the shortcut rule that we've come up with, we just multiply that negative 1 in front, and we're left over with e to the minus x again. So we know the shortcut rule here, that dx of e to the minus x is just minus e to the minus x. So I'm just going to put these values in here. And I can multiply the x by each one, right? I can sort of distribute the x across. We also know, by the way, that the derivative of a sum is the sum of the derivatives. So I know that when I differentiate this, I just add up the derivatives. Okay. So I now have x multiplied by e to the x, that was this first derivative, minus x e to the minus x, right? That's the x multiplied by the derivative of this guy. Minus, well, there's just a 1 here, so we can just ignore that. And I can now distribute this negative sign across. So I have minus e to the x minus e to the minus x. Okay, and that's my derivative. That's as far as I can go. I don't see that I can really simplify this any further. Okay, so again, I used the shortcut rule for exponentials and the quotient rule all together. So now let's look at number 4. So in this case, I have not only the derivative of the exponential that I have to use, but I also have, well, sort of a chain rule thing going on here, right? Sort of the outside is a chain rule because I've got something quantity squared, okay? So we can do this. Let's go ahead and differentiate y. But notice that my variable is z, so I'm going to write this as a dy dz. And again, I'm going to use chain rule. Remember that chain rule works like an onion, right? We take the derivative of the outside part multiplied by the derivative of the inside. Okay? So what I'm going to get here is the outside is something squared. So the derivative of that is just going to be 2 multiplied by that something again, which is going to be this stuff. Put it back in there. Okay? Multiply that by the derivative of that stuff that's inside of there. But here we have to use not only the fact that the derivative of the sum is the sum of the derivatives, but also we have to know what the derivative of this is. We actually kind of did an example like this very shortly, or not long ago, I should say. That is the derivative with respect to z of e to the minus z squared is equal to, well, in front we've got the derivative of this function up here. The derivative of minus z squared is minus 2z, right? And we're left over with e to the minus z squared. Right? So that's my derivative. And of course, the derivative of 2z is simply just 2. So I now get the derivative over here is going to be 2 minus 2z e to the minus z squared. Okay? So let's make that look a little nicer. I'm going to put this value back in. And I now have 2 multiplied by the inside stuff, which is 2z plus e to the minus z squared. Well, really what I do here is I reduce the power by 1, but 2 minus 1 is 1, so the power is 1. There is a 2 multiplied here, right? This is the 2 part here, minus 2z e to the z squared. So actually, if you think about it, I can factor out a 2, right? There's a common 2 here and here. So if I factor that out of this, I get a 1 minus z e to the minus z squared. Okay? This is a 2. And that means, of course, I can combine these 2's together. So in the end, it looks like we have something like 4 multiplied by 2z plus e to the minus z squared multiplied by 1 minus z e to the minus z squared. Okay? So now we've used the chain rule along with the shortcut rule for exponentials. And here we go, we have our solution. Let's look at some more examples. So now let's focus on some logarithmic functions, and we'll combine these in different ways so that we can practice with the different shortcut rules. So let's look at the first problem here, number 5. Notice that we've got the logarithm of some root here. The best way to get at this is to use properties of the logarithm. Well, let me show you what I mean. Let y be equal to logarithm of, this can be written as x plus 5 to the 1/2 power, right? So this is x plus 5 raised to the 1/2 power. But again, because of the properties of logs, we know that if I take the log of something with a power, the power comes down in front, and we're left with the log of the base. So the result would be 1/2 natural logarithm of x plus 5, right? Okay, so that simplifies things right away. Now I can go ahead and differentiate this using the shortcut rules that we know about, and it's far easier to deal with. In particular, I know that the derivative of y with respect to x, well, we have a constant out here, but we know that by properties of differentiation, constant multiplied by a function, we simply ignore the constant, we just multiply that by the derivative of what's left over here. So this is going to be equal to a 1/2, and we have to multiply that by the derivative of this natural logarithm of this particular function. Now this is a function of x, so we have to use our chain rule definition of the natural logarithm. Well, look, we can compute this by taking the derivative of the inside. Well, the derivative of this inside function is just going to be 1, right? Because the derivative of x plus 5 is 1. Divided by that inside function, which is x plus 5, as we can see. So in fact, this is going to be my solution, right? We can write it in a slightly better way. It's 1/2 times x plus 5. Okay, so this is going to be the derivative of log of square root of x plus 5. Let's look at the next example. Notice in this case, I have a quotient. So I'm going to invoke the quotient rule to compute the derivative of this function. Let's go ahead and do that. Here's number 6. So the derivative of y with respect to its input, which happens to be called u, is going to be equal to, well, now again we have to use the quotient rule on the outside and the derivative of logarithms on the inside, right, as we do that. So when I differentiate this, remember that the way I do this for quotient rule, it's going to be a quotient. It's going to be low d high minus high d low over the bottom squared. We go again. Okay, so I'm going to identify the pieces. The top is the high. The bottom, of course, is my low function. So again, low d high. So low is u cubed. D high is, well, its derivative of log is just 1 over that input. So this is going to be 1 over u minus, so low d high minus high, which is log u, d low. Okay? And the derivative of u cubed with respect to u is, well, that's just a power rule thing. So we're just going to get 3u squared, right? And we divide by the bottom squared. So it's going to be u cubed squared. Over the bottom squared we go. Okay, so now I just have to simplify this so it looks a little bit nicer. Now notice I've got a u to the, well, again, if I'm squaring something with a power, remember that I multiply. So this is u to the 6th power on the bottom. One of the u's cancel here, right? One goes away, so there's 2 left over. So I get a u squared minus 3u squared natural log of u. Okay? This u is inside of the log function. Now notice that I have 2 u's that are common here, so I can factor that out of the numerator. So I've got u squared that comes out of the numerator. I've got here 1 minus 3 log of u divided by u to the 6th. And now I can definitely cancel out some of these u's, right? This one goes away, and 2 of them go away here, so I have 3 left over. So when all the smoke clears, the solution to the derivative, or I should say the derivative of this function, is going to be 1 minus 3 log u divided by u cubed. Right, there's my answer. Okay, and again, we used a combination of the derivative of log shortcut and the quotient rule. Now let's look at some examples that combine exponentials and logs. Okay? So in the first example here, number 7, I've got y is defined as e to the x squared log x. Okay, so I have to use the shortcut rule for exponentials, for logs, and the product rule, right? Because I have a product of these 2 functions. Let's go ahead and do that. So dy dx is going to be equal to, again, by the product rule, we take the derivative of the first function, multiply it by the second, plus the other way around. Okay? So the derivative of this first function, again, we're going to use our shortcut rule for exponentials. We get, well, remember, if I'm taking the derivative here, my little f of x is up here. That's a function of x. We've got x squared. So the derivative of x squared is 2x. So that comes down. And then I'm left with e to the function again, which is e to the x squared, multiplied by that other function, right? So I took the derivative of the first, which is this, multiplied by the second. There it is. Plus the other way around, which means just e to the x again, or e to the x squared, I should say, that one, multiplied by the derivative of the second. Well, the derivative of the log of x is easy, right? It's just 1 over x. And so now I can sort of massage this to make it look a little bit nicer. Okay, so in particular, what do I have here? Let me write it out in full detail. I've got 2x e to the x squared log x plus e to the x squared over x. Okay, so this now is my solution. This is the derivative of this function. I used, again, the product rule and the shortcut rule for both exponentials and logs. Let's look at the next example, number 8. In this case, I've combined exponentials and logs as a quotient. So not only will I need to use the exponential and log shortcuts, but also the quotient rule. So if I differentiate this, that is differentiate y with respect to its input x, I would like to remember what the quotient rule is. So I'm going to go ahead and label this as my high function, and this is my low function. And if you remember the quotient rule, it says the derivative of the quotient is, again, low d high minus high d low over the bottom squared we go. So low, which is log x, d high, well, the derivative of e to the x is e to the x, so that's e to the x, minus high, which is e to the x, d low, well, the derivative of log of x is 1 over x. Over the bottom squared we go, so log x squared. And now, again, this is fine except for the fact this is really a complex fraction. Remember that a complex fraction is a fraction within a fraction, so we don't like that. I don't like this 1 over x bit here. So I'd like to massage this a little bit so that I don't have a complex fraction anymore. Notice, as a first step, that the numerator has a common e to the x, so I can factor that out. I've got log x here minus 1 over x all over natural log of x, quantity squared, right? Now, also, with this stuff inside of the parentheses in the numerator, I can get a common denominator, right? You can do this any way you want, but one way to think of this is some quantity, and I'm going to write this in terms of a single fraction. So to do that, definitely you're going to get x on the bottom. You're going to get x natural log of x minus 1, right? That's rewriting this stuff here as a single fraction. There it is. So I'm going to do that. When I do that, I can write that down. I get e to the x, and then inside of those parentheses, I now have x log x minus 1 over x, all over natural log of x squared, okay? Now, look, I have a 1 over x that's really common here, so I can factor that out as well. So when I do that, I now have 1 over x e to the x over natural log of x squared. So I'll sort of just erase this. Okay, this is still x log x minus 1 all over log x squared. Okay, well, this was over log x squared. So it's a little jumbled, but all I did is I wrote this quantity here as a single fraction. Then I factored out the 1 over x. So that's why I've got the 1 over x here. What's left over is an x log x minus 1, which is that, and it's still over log x quantity squared. Okay? And now, because this 1 over x is multiplied by really the entire numerator, I can think of this as multiplying the entire quantity. Okay? So that means I can rewrite this finally, when the smoke clears, in a more simplified way, so it's not a complex fraction anymore. In particular, I can write this as e to the x outside of x natural log of x minus 1 divided by x natural log of x quantity squared. Okay, so when all the smoke clears, I now have my solution in terms of a non-complex fraction. Ultimately, we just used the shortcut rules for exponentials and logs along with the quotient rule. The last bit was all about algebra, okay? But ultimately, this is the derivative of number 8.